Hey, welcome to Deja Vu. It's Algebra 2. As always, I'm your host, Kevin Corpy. Now today we got a great, awesome episode for you today. In fact, it's not awesome, it's radical. We got a radical program for you today. It's lesson 24. That's 6 times 4, 8 times 3, 12 times 2. Lesson 24 is all about radical functions, radical expressions, and at the end we're going to even look at radical equations. One you're not going to want to miss. So, download those worksheets from the district website, www.newbraunfels.txed.net. Enter, and grab a sharp pointy pencil and stick around for about 30 minutes and learn some radical stuff with me today. What do you say? Now, let me start off by asking you, the viewers at home, what is the square root of 25? Huh? Square root of 25. Did you say 5? If you did, great, because that is an answer. That is an answer. It's not the only answer. What's the other one? Is there another one? Well, there is actually another one. But most people tend to forget about it. Okay? Now, if you think about what the definition of a square root is, we're really asking this when we ask the square root of 25. We're asking what number, when you multiply it by itself, when you square it, gives you 25. The square root is the inverse operation of taking the square root. So, definitely 5 times 5, or 5 squared, is 25. So it makes sense that the square root of 25 would be 5. But there's another number that when you multiply it by itself gives it 25. Did you think about negative 5? Negative 5 times negative 5 is positive 25. A negative times a negative is a positive. Therefore, the square root of 25 is, we say, the conjugate pair, positive 5 or negative 5 or plus or minus 5. There are two solutions to the square root of 25 because there's two numbers that when you multiply by themselves give you 25. Okay? That's an important concept of a radical or a square root. Now, let's look in general about what a form of a radical will look like, because it doesn't have to be the square root. I can talk about the cube root, which is the inverse of cubing a number. I could take the fourth root. I could take the fifth root. So we've got a general format right here for a radical expression. It's not an equation yet. We have the root index, which we're going to call n. And it's written right here. There's a little v right here. It's almost like a little nest, and the root index is going to be placed inside there. The actual symbol itself that has this little flare on it that creates the nest for the root index is called the radical. The radical is the symbol. The thing that you're taking the radical of is called the radicand. So we got the radical, the radicand, and the root index. Now, up here when I looked at the square root of 25, notice there was no number written in there. There was no root index. And that's because if there's nothing written in here, it's implied to be a square root. Okay? So if there's nothing written there, it is a square root. If we want any other root other than the square root, we have to specify by writing the n, or the root index, in there. Okay, so this is a radical expression. Okay, let's go ahead and see if we can evaluate some radicals that are not square roots. They have root indices, that's plural of index, that are different than 2. So in this case right here, that's the fourth root of 81. Now that's asking yourself this question. What number times itself 4 times gives you an 81? Ooh, well, if you have your calculator, you could probably figure it out. But let's do it with our own mental capacity here. You can start with small integers like 1. 1 times 1 times 1 times 1 is 1. So it can't be that. It's got to be bigger. 2 times 2 is 4. Times 2 is 8. Times 2 is 16. So it's not 2. What about 3? 3 times 3 is 9. Times another 3 is 27. Times another 3, 27 times 3 is 81. Aha! So the fourth root of 81 is 3, because 3 to the fourth power is 81. Is there another one, though? What about negative 3? Negative 3 times negative 3 is positive 9. Times negative 3 is negative 27. It's negative again. But times another negative 3, negative times negative is positive. So yes, we have another conjugate pair, plus or minus 3. And that's because it's a fourth root. Anytime you have fourth roots or square roots or sixth roots or eighth roots, you're going to be able to pair up your factors, okay, because it's an even number. And that means if you have a negative number times a negative number paired up, it's going to be positive. Negative times a negative is positive. So basically, anytime the root index is an even number, like 2, 4, 6, 8, 10, 12, you're going to have this conjugate pair, the positive and the negative number. Remember that. Let's look at this. The cube root of negative 125. That is, what number times itself 3 times is negative 125? Well, you might get a feel for it. It's got to be bigger than 3, because 3 times 3 is 9. 9 times 3 is 27. 4 times 4 is 16. 16 times 4, it's not 125, it's 64. So maybe 5. 5 times 5 is 25. Okay, 25 times 5, that's 125. But it's not negative 125. So in this case, if I look at negative 5, negative 5 times negative 5 is positive 25. Positive 25 times another negative 5 makes it negative 125. So when you have an odd root index, like a 3, or you have a 5, we don't look at root indexes of 1. An odd root index can actually have a negative under the radical, because we can achieve negative numbers, because an odd number is going to have an even pair, which makes it positive, and then we'll have the one odd man out, which can make it negative. But it doesn't have to be. But in this case, there's only the one number, because 5 doesn't work. 5 makes it positive. All right, what about this one? The 6th root of negative 729. Ooh. Well, that's taking the 6th root of a negative number. That means that some number times itself 6 times has to be negative. Negative times negative is positive. Negative times negative is positive. Negative times negative is positive. You can't take an even grouping or an even number of odd numbers, multiply together to get a negative number. It doesn't work, because you're always going to be pairing them up in 2's, which is going to make it positive. And that's exactly why, if your root index is even, you can't take an even root of a negative number. So this would be no solution. There is no number that when you multiply by itself 6 times will give you a negative. Now remember, it worked for 3. 3 was an odd number. So we can multiply and get an odd number when there's a negative number when there's an odd number of them. But when there's an even number of factors, we can't get a negative. All right? Now, let's throw all those negative things in and look at this one. This is kind of daunting. That is the negative square root of 4 to the negative first. Well, we talked about negative exponents on a previous show. That's the same as the negative square root of 4 to the negative first is 1/4. So what does that mean? That means, since the negative is on the outside, that our answer will be negative. It's different from being on the inside. Now, what's the root index? There's nothing written, so it's implied to be a 2. That means what number times itself, okay, one number times itself gives you 1/4. Well, 1/2 times 1/2, or 1/2 squared, is 1/4. So the square root of 1/4 is 1/2, and we're like multiplying that final answer by a -1. So our answer is negative 1/2, because the negative was on the outside. Had the negative been on the inside, it would have been no solution, because we'd have a negative under a radical, and our root index is an even number. Okay, got it? So, even root indexes, no negatives under the radical. Now, even though that was a negative, it was an exponent, not a negative number. Odd root index, 3 negatives under the radical. Okay, got it? All right, let's look at some basic properties of radicals. There's 2 that we're going to look at. The nth root of a product, AB, we can give them each their own radical. That's the same as the nth root of A times the nth root of B. And same thing for division. The nth root of A over B is equal to the nth root of A over the nth root of B. So what we could have done over here is I could have used that property on the square root of 1/4. I could have called that the square root of 1 over the square root of 4 by this property here. And then I would have made it into 2 smaller problems. The square root of 1 is 1. The square root of 4 is 2. Now in this case, I don't want to take the plus or the minus, because the negative there was specified that I wanted just the negative solution. Okay, so that's called an indicated root. Let's use those 2 properties, though, to simplify this expression. We've got the 4th root of 16 times x to the 8 over 5. We have 2 factors in the numerator. We have 1 factor in the denominator. Each factor gets its own 4th root. So let's write it like that. That's the same as the 4th root of 16 times the fourth root of x to the 8 over the fourth root of 5. Well, let's see what we could do with that. The fourth root of 16, what number times itself 4 times is 16? It's going to be 2. Did you say that? 2 times 2 is 4, times 2 is 8, times 2 is 16. Now, because there's nothing specified there, you might want to put plus or minus 2. So this can actually simplify to a positive or a negative ratio. The fourth root of x to the 8, that one's going to be a little bit trickier. What number, when you raise it to the fourth power, gives you x to the 8th? Well, remember the property of exponents. It says x to the a power raised to the b power is x to the a times b power. You multiply when you're raising a power to a power. So if I take x squared and I raise it to the fourth power, that's going to give me 2 times 4, which is 8. So the fourth root of x to the 8th is x squared. I'm going to show you a little bit easier way to do that here just a little bit. All over the fourth root of 5. Well, the fourth root of 5 is not a nice integer value. There's no number when you multiply, or integer that is, when you multiply by itself 4 times gives you 5. 1 is too small, 2 is too big. So that number we just leave as the fourth root of 5. Now, depending on your teacher, they may discourage having radicals in the denominator. And if that's the case, you need to get rid of it by multiplying by clever forms of 1. And in this case, since it's the fourth root of 5 and I have one of them down there, here's what I'm going to have to do. I'm going to have to multiply by the fourth root of 5 over the fourth root of 5. That's really equivalent to 1. Anything divided by itself is 1. I got to do it again. That's the fourth root of 5 over the fourth root of 5. And then I do it one last time. The fourth root of 5 over the fourth root of 5. And here's why. Notice in the bottom now I have the fourth root of 5 times the fourth root of 5 times the fourth root of 5 times the fourth root of 5. Well, if I have 4 of them and I'm taking the fourth root, it's like having the fourth root of 5 raised to the fourth power. And since they're inverses of each other, I'm just going to get a 5 in the denominator. Had this been the cube root of 5, I only would have needed 2 more to make 3. Had it been the fifth root of 5, I would have needed 4 more to make 5. Okay? Now look what I have in the top. I have plus or minus 2 x squared, and now this is the same as the fourth root of 5 to the third power. So we can leave it like that. So there it is. Takes a little bit of practice. It's using the rules of radicals right here, but start small, work up big, and key is just to practice. Okay, so remember I just told you there's an easier way to handle the, the fourth root of x to the 8. It's going to be a lot easier, but it's going to involve something new, so I hope you're into learning new things. This is called a rational exponent. Now remember we talked about rational numbers on previous shows. A rational number is nothing more than the quotient of two integers, like 1/2, negative 2/3, so on and so forth. So we can have those numbers as exponents as well. Now, where are they going to come from? Well, here's where they come from. If I have this right here, the nth root of a to the m power, that is the same as a to the m divided by nth power. Okay, you got that? What does that mean? That means that I'm raising it to the mth power, but I'm also raising it to the 1 over nth power. I'm dividing by n. So the root index right here, if it's an nth root index, becomes an exponent of 1 over n. Or if you want to look at it without the m, we could say that the nth root of a is equal to a to the 1 divided by nth power. That's important. So we take the root index, we take its reciprocal, and it becomes the exponent on the radicand. And if there's already an exponent there, then it becomes the numerator of that fraction. Because remember, I'm raising a power to power, I multiply. Well, it doesn't matter if I have the m under the radical and then take the nth root. I can actually take the nth root and then raise it to the mth power. Because when I'm raising a power to power, I'm multiplying, and multiplying is a commutative operation. So remember this. Notice in the exponent here, the n is in the denominator. It's below, it's down underneath the ground essentially, if you call this bar the ground. So it's the root. It's underneath. It's the root, so it's the root index. And m is still in the numerator. It's the exponent on a when you're converting it back. Let's try this. Let's write the square root of x quantity cubed as a rational exponent. Well, let's work from the inside out. This is the square root of x. So remember, the root index is 2. So by our rule, that's the same as x to the 1/2. And all that is raised to the third power. And now when I'm raising a power to a power, I multiply. So that becomes x to the 3/2. There you go. So x to the 3/2 is the same thing as the square root of x cubed. Got it? Pretty cool. Let's try this one here. Well, the first thing I'm going to do is split this up. I have a product, so that's the 4th root of 16 times the 4th root of x cubed. Well, the 4th root of 16, if you can evaluate it, it's probably easier in radical term. So that's good 2. We saw that previously. 2 times 2 times 2 times 2 is 16. But if I want to write the 4th root of x cubed as a rational exponent, that's going to be x cubed divided by 4. So it's 2 times x to the 3/4 power. The root index was 4. It's the denominator of my exponent. It was raised to the 3rd power, so it's still an exponent in the numerator. All right, now let's work backwards. What if I have negative 125 raised to the 2/3? Can I evaluate that? Well, I have two options. That's the same as negative 125 squared, which makes that a huge number. And then I can take that number and take the cube root of it. Or, since multiplication is commutative, I could take the cube root of negative 125, do that first, and then raise that to the 2nd power. Okay, let me show you exactly why that is. That's the same as negative 125 squared to the 1/3, right? And I multiply 2 times the 3rd, I get 2/3. Or it's the same as negative 125 to the 1/3, and then I square that. That's still 2 times the 3rd. But the order in which I do that is different. By raising it to the 1/3 first, I'm making my number smaller, and then I'll square the result. So if you have the option, take the root index first, if you can, make the number smaller, and then make it bigger, especially without a calculator. Now the cube root of negative 125, we already discussed, was negative 5. And so now I can square that number. Negative 5 squared is positive 25. And that's your answer. Now notice if you would have gone negative 125 squared, you'd probably still be trying to figure that out. And then once you got that huge number, good luck taking the cube root of it. It would have ended up being 25. Okay? So go small before you go big. Let's take a real quick break, but don't go anywhere, because I'm going to be right back before you know it. Watch these public service announcements, and while you're doing that, think about this. What does the square root of negative 4 and a ceramic tree have in common?
The odds of a child being diagnosed with autism, 1 in 150. To learn the signs of autism, go to autismspeaks.org.
Welcome back to Deja Vu. It's Algebra 2. I'm your host, Kevin Corpy, talking to you today about some radical functions, radical expressions, and soon to be radical equations. Now, what do the square root of negative 4 and a ceramic tree have in common? Think about the answer. It is that they both have imaginary roots. Back to the math. Okay, so let's go ahead and look at what a radical function is. A radical function, as you might imagine, is just a function that contains a radical expression in it. And we're going to be looking primarily at the square root function, which is a root index of 2, and it's going to contain a radical, a square root of x. All right, now, what does the graph of f of x equals the square root of x, which is the function form, what does it look like? Okay, one thing before we look at the graph, notice since the radical is in the problem, it has a plus sign implied that's there. So there is an implied or indicated root of positive solutions there. If the root is there, we take the indicated root already. If we are introducing a radical, we have to remember to take plus or minus. That's an easy way to remember it. So this would be just the positive square root. Let's see what it looks like. Back in Algebra 1, you can figure out what a function looks like by creating a table of values. You choose some x values, anything will work, and then you plug them into your function, and you get ordered pairs and you plot them. Well, I'm going to choose my x values very carefully. I want to take the square root of my x values, and I don't have a calculator with me, so I'm going to choose values of x that are perfect square, 0, 1, 4, 9, 16. When you plug those in, the square root of 0 is 0, so I get the point 0, 0. That means that my function will pass through the origin. When I look at the point 4, square root of 4, which is 2, I get the point 4, 2. So over 4 up 2, and of course the 1, 1 is in there as well. Let's jump down here. If I plug in a 16, the square root of 16 is 4, and notice it's just positive 4 because it's the indicated root. And it's off my graph, but it would be somewhere out here. The square root of 9 is 3. Now that we have these points, notice it's not a straight line. I try to connect the dots with a nice smooth curve. And that's what the square root of x looks like. Notice that it almost looks like part of a parabola turned sideways, right? If I was to stretch this out here. And that's no coincidence, because the square root and x squared are inverse operations. They're also inverse functions. Now, notice if I was to take the plus or minus, if I was to look at plus or minus 1, plus or minus 2, plus or minus 3, I would, at those x values, create some other y values that would plot down here. And I would get this entire graph. Well, remember, a function, by definition, can only have one output per input, or it has to pass the vertical line test. So if I was looking at the plus and minus, I would fail the vertical line test, which is why for the function, since we're finding these to be y values, and we can only have one y value per input, we take the indicated root, which is positive. If I was interested in the negative version down here, remember what that would involve? It would involve reflecting the graph across the x-axis, which would put a negative in front of my function. All right? So let's look at graphing transformations of that parent function. Any transformation we're going to sketch is going to be of the form a times b inside the radical times the quantity x minus c plus d. And if you remember, a is just your vertical dilation. It's the stretch. It's vertically taller or narrower. And if a is negative, it's an x-axis reflection. B is your horizontal dilation. And what that's going to do, it's going to stretch it horizontally, opposite of what it appears. C is your horizontal shift. It'll take it left or right. And then D, outside, is your vertical shift. So the same transformations that we did earlier in the year on quadratics are going to be the same ones that work on this function. Everything affects the graph the same way. We just start with a different graph. Let's see if we could do that for this function. We'll call it g of x equals 1 minus 2 times 3 minus x. Your first step is to put it into standard form, which is this form right here. Okay, so I want my a to be in the front. I want this plus 1 to be my d in the back. So I write that as negative 2 square root of. Now notice I need to have an x minus c, and any coefficient of x needs to be factored out. So first thing I need to do is rewrite that negative x plus 3. So my x is first. And then remember that plus 1 that was in the front, I put it at the back. Well, now notice I have a negative x. I want it to be a positive x. So at this point, you want to factor out any coefficient in front of the x. In this case, it'll be under the radical, which is a negative 1. So that would be an x minus 3, and then plus 1 out there. So what are the transformations? The negative in front is my a. It's going to be an x-axis reflection, and the 2 will stretch it vertically. The negative here is my b. That's going to be a y-axis reflection. The x values are switching. The minus 3 takes it to the right. The plus 1 moves it up. So right 3, up 1. So what you might want to do is get a real basic idea of what your parent function looks like, and that's this, the square root of x. Remember, you have to do your dilations and reflections first. It's kind of a sequence. So the negative would reflect it down, so I'll draw that as a dotted line. We're also going to stretch that now by a factor of 2, which makes the graph a little bit steeper. Now this negative will take that graph and reflect it across the y-axis. So I take that graph and reflect it. And notice it's still anchored at the origin. So this graph right here now, which is steeper than the square root of x, but opening down into the left, is my basic shape. Now if I can move that shape, right 3 and up 1, I've got it. Well, since I'm still anchored at the origin, that's the best point to follow. So here's my final graph. My origin is going to be 1, 2, 3 to the right and up 1, and I'll anchor it there, and now I just follow that basic shape. Now one thing you could do as a word of caution as you're drawing this, you're going to be crossing the y-axis. Y-intercepts are easy to find for functions. Let's see what it is. If you plug it in, you get 3 minus 0, which is 3. The square root of 3 is about 1.7. Times 2, it's about 3.4. 1 minus 3 is a negative number. And that's all you really need to know for a sketch, because you know that it's going to cross below the x-axis. So I'll just draw it with that same basic shape, and it'll look like that. From there, we can find the domain. The domain is going to be everything less than or equal to 3, right there. And the range is going to be everything less than or equal to 1, everything below 1. This will continue to go down to negative infinity. And that's a crude sketch by hand, but it's enough to get your basic graph and your basic domain and your basic range. Transformations, hugely important. Memorize your new parent function. Now it's time for
Deja Review.
All right, for Deja Review, I'm going to kind of review some of the skills we just looked at, but I'm going to look at it in the context of what's called a radical equation. Here we have a radical equation. It's the square root function, square root of x plus 18, and it's equaling x minus 2. This is a conditional equation, and that means we're trying to solve it. We want to find the values of x that when we plug into both sides give us a true statement. One method is guess and check. Pick a number, plug it in, see if it works. Okay, it's kind of taking shots in the dark, so we won't do that way. Okay, we're going to try and find a systematic way to do it. And the way we solve radical equations is this, by hand, algebraically. Number one, you want to isolate the radical. And what does that mean? That means you want to get it all by itself on one side of the equation. Well, notice that it already is. If you had two radicals, since you have two sides of the equations, separate them, one on one side, one on the other. Okay, once you have your radical isolated, step two is to square both sides. And that's if you have a square root radical. If you had a cube root radical, you want to cube both sides, so on and so forth. So whatever the root index is, you want to raise both sides to the reciprocal of that root index power. All right, so let's go ahead and do that. So if I square both sides, and I'll show that here, I'll show that here. Now we carefully have to work. Well, by design, the square root of something squared, since those are inverse operations, will undo each other, and we're just left with the radicand. And on this side, I have a binomial squared, which we have to expand. So squaring a binomial, we can square the first. The quickest way is to multiply those two and double it. So that's minus 2x. Doubled is minus 4x. And then negative 2 squared, the last one squared, is plus 4. Notice my radicals are gone. Okay? If you still had a radical at this point, you would go back to step one. So it's a process of isolate the radical, square both sides. Isolate the radical, square both sides. Okay? It's like washing your hair. Okay? Lather, rinse until you feel good about it. Once your radicals are all gone, then you're ready to solve it algebraically. Notice it's a quadratic equation now. And we solve quadratics algebraically by getting everything on one side. So I get x squared, that'll be minus 5x, and when I subtract, I get negative 14, and that equals 0. Now that factors into x minus 7, x plus 2, remember factoring, and now the zero product property tells me that x has to equal 7, or x has to equal negative 2. But wait, hold the fort. There's one thing that you have to be aware of when you're solving radical equations. You must test your final answers, because you might get something that's extraneous. And here's why. We're starting off with the radical function. Remember, radical functions can only have one x-intercept, right? If you remember your parent function, if you shift this guy around, it can only cross the x-axis once. But by squaring it, we're making it a quadratic. And a quadratic can have two x-intercepts, just like this. There's my v, okay? So one of those might be an imposter trying to sneak into the solution club. We call him extraneous. He's a solution to the quadratic, but not the original radical. So test your solutions for radicals. And how do we do that? We plug it in. So let's try 7. 7 plus 18 is 25. The indicated root is positive, so the positive square root of 25 is positive 5. What is 7 minus 2? 5. Does 5 equal 5? Yes. Welcome to the club, 7. What about negative 2? Well, you got to be careful. I squared both sides in the original problem, but you got to plug it back into the original problem before you've messed with it at all. If I plug in a negative 2, 18 minus 2 is 16. The indicated root is positive, so the positive square root of 16 is 4, positive 4. When you plug a negative 2 up in here to the right side, negative 2 minus 2, that's negative 4. Does 4 equal negative 4? No, those are about as opposite as you can get. They are, in fact, opposite. So we caught an imposter. He was trying to sneak into our solution club, but we met him at the door, kicked him out. We only have one solution, and it's 7. So check for extraneous when you square both sides of a radical equation. That's all the time we have on today's show. Another 30 minutes come and gone, but filled in between with lots of good information, and I hope you absorbed it. If not, feel free to tune in again. It's going to be showing all through the week. Send me an email if you have any questions about today's episodes, and hopefully I'll see you again next week, right? Until then, I am Kevin Corpy reminding you to do your homework.